Good evening everyone, I am Nasim Parvez. Today I will present my research title Early Diabetes Risk Detection using Smartphone Sensor and LSTM-GAN Framework. This study explores how the smartphone sensor data and artificial intelligence can help detect diabetes risk early without using blood tests. Today I will discuss about background of the study, research scope, problem statement, scope of the research, research review, methodology, results and future work. Let's start with background. Background of the study. Diabetes is one of the fastest growing health problem in the world. According to the International Diabetes Federation, nearby 800 million people may have addicted diabetes by 2027. Diabetes can cause serious health problems such as heart disease, kidney failure, liver damage, and so on. Currently, diabetes is usually diagnosed through blood-based tests such as fasting glucose test and A1C tests. Now I will discuss about research gap. Many human activity recognition studies focus only on identifying activities such as walking, running, or sitting. However, they do not focus on predicting chronic disease like diabetes. Most existing models are tested on clean benchmark datasets which are different from real-world conditions. Existing smartphone-based diabetes systems often have three major limitations. First, they lack personalization. Second, they do not clearly explain why a person is considered at risk. Third, they have limited clinical validation using A1C test results. Although GANs have been used for data argumentation, they are rarely applied to clinically validate diabetes risk estimation. Now, problem statement. Current diabetes detection methods have several problems. They are invasive because blood samples are required. They are episodic because testing happens only occasionally. They are expensive and not suitable for continuous monitoring. Therefore, the main question of the research is how can we detect diabetes risk early using only smartphone sensor in a non-invasive and continuous way. To solve this problem, this research combines LSTM deep learning, GAN based data argumentation, cosine similarity risk scoring, and clinical validation using A1C results. Now I'm talking about scope of the research. This study focused only on smartphone sensor, specifically accelerometer and EGC data. We monitored 21 different activities such as walking, cycling, climbing series, sitting, and laying down. The data was collected continuously for 30 days. The study used data from 130 diabetes subjects and 3 experimental subjects. The main output are activity intensity classification, heart rate prediction, diabetes risk estimation, and correlation with A1C test results. Other diseases and wearable devices are not included in this study. Now I'm talking about Research Review Part 1, HAR Evaluation. Let's look at the evaluation of human activity recognition methods. Earlier studies used machine learning algorithms such as KNN, SVM, and random forest. These methods struggled with noisy sensor data and temporal patterns. Later, deep learning methods such as CNNs and LSTMs improved accuracy. However, most studies used benchmark datasets instead of real-world data. Smartphone-based diabetes systems improved accessibility and still lacked personalization and A1C validation. No previous study combined LSTM, GAN, cosine similarity and A1C validation together. This is the key gap addressed by our research. Now, review part 2, GNNs and risk. GNNs are powerful tools for generating synthetic data. Several studies such as guided GNN and Thera GNN successfully generated realistic sensor signals. GNNs help improve model robustness when data is limited or noisy. Research also shows a strong relationship between physical activity and diabetes risk. Cosine similarity has been used in healthcare for profile matching. However, it has rarely been used to estimate diabetes risk from smartphone sensor data. This creates another opportunity for our research. Now, methodology overview. Our methodology consists of 6 main steps. First, data acquisition. Second, processing. Third, GIN based argumentation. Fourth, LSTM model training. Fifth, risk estimation. And finally, validation. I will briefly explain each step. In step 1, data was collected through an Android application. We recorded accelerometer and EGC data for 30 days. In step 2, we cleaned the data by removing missing values and outliers. We also applied filtering and normalization. In step 3, the GIN generated synthetic sensor data. This increased the dataset size significantly and improved training quality. In step 4, LSTM models were trained for activity classification and heart rate prediction. In step 5, cosine similarity was used to compare each subject's profile with diabetic profile and calculate a risk score. Finally, in step 6, predicted risk was validated using actual A1C measurements. Now I am talking about key hyperparameters. This slide shows the important parameters used in the LSTM models. Both the classifier and riggers are used. 4 LSTM layers, 64 hidden units per layer, Adam optimizer, and learning rate of 0.001. Dropout values between 0.5 and 0.8 were used to reduce overfitting. Different loss functions were used. depending on the task. These settings provided stable and accurate performance. Now let's discuss about result. The activity recognition model achieved an average accuracy of 98.12%. Across different datasets, accuracy remained consistently high. When GAN generated data was added, accuracy improved from 97.12% to 98.17%. This shows the GAN argumentation successfully improved model performance and generalization. Results of heart rate prediction and risk estimation. For heart rate prediction, the model achieved an R-squared value 0.9576. This indicates a strong prediction performance. Risk estimation was based on cosine similarity. For example, subject 1 had a similarity score of 60.24%. This placed the subject in the moderate risk category. The A1C result was 6.1%, which confirmed the prediction. This shows a meaningful relationship between our risk score and clinical measurements. Future work. There are several directions for our future improvement. In the short time, we plan to collect data from more participants and include smartwatch data. In the middle term, we want the system to work regardless of where the phone is placed. We also plan to develop a real-time alert system. In the long term, the framework could be extended to detect other chronic diseases such as hypertension and cardiovascular risk. Privacy preserving on device processing is another work. Privacy preserving on device processing is another important future goal. Conclusion. This research presents a new framework that combines LSTM, GAN, and cosine similarity of early diabetes risk detection using smartphone sensors. The system achieved 98.17% activity recognition accuracy, R-square score of 0.9576 of heart rate prediction. The estimate risk scores showed a meaningful correlation with actual A1C test results. Therefore, this framework provides a low-cost, scalable, and non-invasive alternative of continuous diabetes risk monitoring. However, these are some limitations. The number of experimental subjects was small. Some data was lost due to device crash. Also, phone placement was limited to the pocket position. These limitations can be addressed in future work. Thank you for your attention. I would be happy to answer any questions. Thank you.